Okay, hello everybody. So part A, explain why knowing f of e sub I for the unit vectors e1, e2, e3 up to en is enough to know where f sends any v in Rn, any vector v in Rn, provided that f is linear. So if f is linear, explain why knowing the f of ei is enough to know where f of v is. Okay. So since v in Rn means that v really has n number of components, well then this is just v1 e1 plus v2 e2 plus dot 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 plus vn en. I could, if I want to, I can write that in a shorthand like this. And here each of the vi's is now a real number, whereas v is a vector in Rn. Okay. Now, for example, v equals 4, 2, 3 is just 4 times e1 plus 2 times e2. And I guess this is a 3 plus 3 times e3. So that's what this means. Okay. This is sort of in parentheses to explain this abstract notation. Explain why knowing f of e sub I is enough to know where f sends v. Okay, so then this means f of v is what? Like, we need to figure out what that is. Well, since v is the sum of the vi ei, and since f is linear, then we can pull this summation out, we can pull these scalars out, and we get the sum of the vi's times the f of ei's. Maybe more concretely, f of v1 e1 plus v2 e2 would be equal to v1 times f of e1 plus v2 times f of e2. So this is sort of in parentheses. It's a this is a sum of n terms of or no, it doesn't have to. Yeah, it's n terms. If n equals 2. Okay. So if we know f of ei for each ei, we just linearly combine them via this rule, just by the coefficients of v, with the coefficients of v. The coefficients are just these numbers v1, v2 up to vn. For an example, is like in the plane we have e1 and e2. And if I know that f of e1 is 2, 3, 7, and f of e2 is 1, 1, negative 1, then v being 2, 3 means that f of v is equal to 2 times 2, 3, 7 plus 3 times 1, 1, minus 1. So this is sort of in my head, this is an example. And here this would be a linear map from R2 to R3, because I had 2 unit vectors and then my outputs were 3-dimensional. Okay. That's part A. Okay, part B, where's that? Part B. Demonstrate how this works by defining your own linear map from R2 to R3 and calculating f of v for v equals 2, 3. Wow, did I choose 2, 3? Yes, I did. That is remarkable that I just did that by random chance. Anyway, okay, so you can see how I think is to do an example. So I guess this is part B. I defined, so let me expand on this. To define a linear map from R2 to R3, all I have to do is hand you two vectors in R3, two outputs. Just two outputs, that's it. I don't need to like come up with some crazy formulas, something, something, something. Although I am doing that, the point is that all I have to do is come up with these two. And then if I say that it's a linear map, then you know how to calculate it on anything. So in particular, let's take an arbitrary element, v1, v2, and map it to v1 times 237 plus v2 times 1, 1 minus 1. And, you know, if we want, we can write this in the usual form of like something, something, something. In that form, it's, you know, what's the first something? It's going to be 2v1 plus v2. 2v1 plus v2. The second something will be from here, the second component. That's 3v1 plus v2. And the third component is going to be 7v1 minus v2. And so now I have the usual way that we write down a map by this formula, taking an arbitrary input and saying where it should go. I could put this in a computer and it would be able to draw it now. Okay. That's part B. Part C. Draw a cartoon illustrating B. Draw a cartoon illustrating B, okay. My cartoon will have an input and an output space. Here's my input space. And then here's my output space. And this is a cartoon, so I don't have to draw 2, 3, 7 and 1, 1 minus 1 super well. But I'll just draw some vector. Let's say this is the vector 2, 3, 7. And this vector over here is the vector 1, 1 minus 1. It doesn't even look like this is totally wrong. But it's a cartoon. So E1, E2. And sort of like, if I want to even visualize it more, I could think of this square will go to this parallelogram. And then if I want to even visualize it more, this pink square will go to this, oh wait, hold on. Yeah, this parallelogram. This is getting harder to draw. Etc., etc. And in fact, the entire plane goes over here, but I'm not going to draw the entire plane, so I'll just draw that much. This is part C. Cartoon. Okay. Is there a part D? Oh, there's part D and part E. So part D. Demonstrate how this works by defining your own linear map from R to R2 and calculating f of v for v equals minus 3. Okay, so D. If f from R to R2 is linear, I need only choose f of E1, because my input space is just one-dimensional, so I just have to choose one vector. Okay, how about 2 and pi? Okay, so now what do? I could call this v1, it's a number. I could call it x, or I could just call it v. Let's call it x, why not? X maps to x times the vector 2 pi, which if I want I can write this in the usual way as 2x and pi x. Okay. That's part D. Oh wait, do I have to calculate it on a vector? Okay, so for x equals -3, f of -3 is -6, -3 pi. Right, I think it wanted me to evaluate it, calculate it at a specific input, -3. Of course, I called my input x, but what we call it doesn't matter. Okay, part E, draw a cartoon illustrating D. Part E is to draw a cartoon illustrating this, so I need an input space and an output space. Okay, so somewhere I have 0 on my real number line, and here's E1. And then, F maps things over into two-dimensional space, and it goes to, 2 pi? 2, 3, I don't know, maybe 2 pi is here, 3.14 is the height. And so, in fact, like this entire line would keep going over there. This part of the line back here would go over here. And so the image of this map is a straight line, and this is my cartoon. Right, f of -3, 1, 2, 3. This point is sort of really this vector, and that point would go to 1, 2, 3. So maybe even I'll just label this f of -3 is the vector -6, -3 pi. It's an even better cartoon.